Hello everyone, January the 7th. Alright, let's do this. First question, linked list random node. Alright, we've done this before. Multiple times if I remember. Yeah. Oh, not multiple times, only once. What are these? What? That's interesting. Alright, oh, got the wrong one. So, given a single linked list, return a random node's value from the linked list. Each node must have the same probability of being chosen. Implement a solution class. Initiates the object. Get random chooses a node randomly from the list and returns its value. All the nodes of the list must be equally likely to be chosen. Okay, so get random, get random, get random. It's extremely large and its length is unknown to you. Could you solve this efficiently without using extra space? Isn't this we're going to use reservoir sampling again? Okay, what's reservoir sampling again? I forgot. How do you spell reservoir? Yeah, sampling. Reservoir sampling. I feel like, if I remember correctly, it is to handle random, right? It's to handle, if you don't know the size of the list and you want to pick things randomly. Without replacement. K items from a population of unknown size, right? In a single pass over the items. The size of the population n is not known to the algorithm and is typically too large for or n items to fit into main memory. The population is revealed to the algorithm over time, and the algorithm cannot look back at previous items. At any point, the current state of the algorithm must permit extraction of a single, simple random sample without replacement of size k over the part of the population. I think it feels like this is what we're looking at, right? Okay, I see a sequence of items one at a time. We want to keep 10 items in memory. Select the linked list, and we want them to be selected at random from the sequence. If we know the total number of items n and can access the items arbitrarily, then the solution is easy. Select 10 distinct indices. Yes. The problem is that we do not always know the exact n in advance. So, simple and popular but slow algorithm, R. I don't want this, I want the optimal one. How many items are discarded before the next items enters the reservoir? Wow, a lot of different algorithms for this. What's the general idea? I don't remember. Probably have to go to simple algorithm. Maintaining a reservoir, of size k, which initially contains the first k items of input, and then enter it over the remaining items until the input is exhausted. Using one base index, this be the index of the item currently under consideration, then generates the random number j between 1 and I. Hold on. So I'm currently looking at an item, and I say if I want to pick this item, I have the probability of the new item coming in. Okay, hold on. I might remember. The probability of getting this item is 1 over n, right? And then if we didn't pick it, right? If we did not pick it, then the probability of hold on, so of the next one, not picking the next one, right? The probability of picking this and not picking this should be 1 over n times n plus 1. The probability of not picking the next one. So pick this one, right? The probability of picking this one is 1 over n, and the probability of not picking the next one is n over n plus 1. And then the next one will be so 2 minus n plus 2, n plus, so on here we have n plus 2, right? And the probability of not picking this one, so 1 minus, so it would be n plus 1 divided by n plus 2, and all the way at the end. Okay, so how do we do? So the probability, so if whenever we hit the probability, we pick that value, right? And yeah, so the probability of picking one of the others. So whenever we pick the value, we update the value. If it's not, then it's the 1 minus, right? It's the 1 minus. I think, yeah, exactly, right? Randomly j, between 1 and I, if j is at most k. Selected and replaces currently occupies the j's position. Reservoir discarded. In fact, for all I, the ith element of the input is chosen to be included in the reservoir with probability yes. Well, in our case, the reservoir k equals 1. At each iteration, jth element array is chosen to be replaced with probability this. That when the algorithm has finished executing, each item in the input population has equal probability. Because the first one has this, and then 1 minus, because this is basically we say the next one we don't pick, right? So 1 minus this times 1 minus this. Yes, okay. So yeah, I think this is reservoir sampling. Good. Man, these problems are good because it helps. Right? It helps just to, you know, refresh this memory of, you know, reservoir sampling or these techniques. That could be something we can talk about, reservoir sampling. All right, so we'll have to do. Wait, do we have to initialize it? No, so just self.head equals head, right? So get random. Oh. What if we go to the end? Well, if we go to the end, I guess we just go back to the front. Yeah, so we should have a, say, self.index. Right? Self.index, as I start with 0. And every time we're going to pick rand int. So from random import rand int, I think it's inclusive. So we went from 0 to the current index, right? And then every single time we're just going to check. Shouldn't we go to the end? Hold on. So when we call get random, right? No. What's the probability of picking the first value? Shouldn't that be 1? And then I move on to the second one, so the probability should be 1/2. Right? If I have one value, that will be picked all the time. So we will always return the first value. So we're going to say if self-value is +1, right? We always +1. Oh, +1. Now it's not index. It's self.head. Okay. Self.node equals head. And self.count equals 1. Okay, so first one is if get random, right? And we need to check 1 with 1 to self.count, then we return this value, but we will increment count and put a node to the next one. And the next one comes in and we do the same until we get it, right? Next time do the same. And once we go to the end, we replace. Okay? So while rand int 1 to self.count is not equal to 1, right? Wait, hold on. So I sample, right? I sample this. And then keep going. Wait, do I have to go through all 10 to the 4th to get it? Number of nodes is in this range. Can I just return if I find something? Like every call, we'll just go, boom, if we hit, then we get this value. Right, now we call again, we start from this, we just keep going to the end. Wait. Can we return? I think we have to go to the end. I think we have to go to the end. So we're gonna say res will equal to, I don't know, res can be anything. And then we say node equals self.head. I don't know. I mean, it feels like when every single call I have to go all the way to the end. and length is unknown, we just keep going to the end. If we don't go into the end, and we say just every time we hit one, but the probability is has to go to the end. Yeah, it has to be, right? Rest is node equals this. We say while node, then we say while node, say if. Now we don't need these, right? Rest count. We say if 1 is equal to rand int 1 to count, rest equals no.val, and then just keep going, and then we just return rest. I'm not sure. I'm very, very much not sure. Oh, I forgot to increment. My bad. So if 1 is otherwise count plus equal 1 and node equals node.next. Let's take one random value. Seems right. I don't know. Let's try it. The thing is, you have to. Yeah, that feels slow, right? 208. So this is reservoir sampling. My question, yeah, we cannot like prematurely stop it. That's what I think. But I think we have to go through the entire linked list to produce each random value. It is not correct to stop prematurely. Yes, to stop prematurely. And this is ON. And this 208, 22. All right, so what happened to these 80 millisecond solutions? I guess just use choice. Turn that into a array and use choice. You have 2 peaks. Steps. But you need a length. You need a length. All right, we get a length. This is to get a length. This is to get the length. But if the length is gigantic, or it's, how should we say it? If it's a stream, right, and we want to return something at a current, we just stop at current, but if we want to get the next one, we'll have to go from the start. This probably is the reservoir sampling as well. Let's take a look at the solution. I forgot. It is reservoir sampling. Convert into an array. Yeah, that would be fast. Because every check is O1. It requires space. Yes. Yes, that's true. At any given moment, yeah, that's the thing. If we want to get any given moment, that we need reservoir sampling. Simple and slow one. Ah, this is from Wikipedia. Scope, chosen value, that is count, current, wow, current. Random is smaller 1 divided by random. That's fine. Yeah. That's true. Like if you don't know, it's just it's not gonna work, right? Oh, look at this. This is my comment. Current value returned. Infinite loop. Yeah, exactly. So that was I see. That was my idea. Yeah, it makes sense, right? It makes sense. I mean, you have to go all the way to the end, but in this case, you don't, right? You don't. You don't stop halfway. You have to go all the way to the end. So why reservoir sampling? But as a practice for reservoir sampling, this is necessary. But in this particular case, it's not. Now I see. But well, let's call it a day. Because the other method is very straightforward. You just get the count, and we're done. As a practice for reservoir sampling, but that's not the best way. All right, let's take a look at this. A gene string. Okay. Suppose we need to investigate a mutation from a gene start to a gene string end. Start and end, where one mutation is defined as one single character change. Yeah, that's called a SNP. There is also a gene bank that records all the valid gene mutations. A gene must be in the bank to make it a valid gene string, given the two gene strings, start and end. and the gene bank return the minimum number of mutations needed to mutate from start to end. If there is no such mutation, return starting point is assumed to be valid, so it might not be included in the bank. Wait, what does the bank do then? One mutation is defined as one single character change. Yes, I know. We changed the A. There's also a gene bank that records all the valid gene mutations. Oh, so you can only do mutations this way. So all the valid gene mutations. A gene must be in the bank to make a valid gene string. So from one position, one state to the next state must be inside the bank. And once we're inside the bank, then we just try to see if we can get to this from within the bank. Does that mean the end must be in the bank? Okay, start end or 8. Bank has the most 10. But here, this one's inside. This AAA, C, GGT, yeah, that one is this one. So this one doesn't have to be in. So we just want to see mutations, right? So from here, I can only mutate to this one. I cannot mutate to this one because this requires 2 mutations, right? And I cannot mutate to this one. It requires too much. So I mutate once to this, right? We turn the last one to A. And then from this, I can turn to this. I can turn C into A. Ooh. So what are you saying? A graph, right? We need a graph to see how the genes connect to each other. But how do we do this graph? Well, I mean, only 8 characters, so we can just check, right? So for this and everybody, so the start is the node, right? In the start, we can go out to any one of these that allow us to have, right? And from each one, we're gonna go to all the rest. Yeah, we go to all the rest. But remember, the first step has direction. But then we don't have direction. The first we have direction. So you know what? That should be the last step. We should first identify, right? Identify the graph within, right? So from one, if I can connect to the other, then it should be it's a directional, right, graph. And then, for instance, this can connect to this, right? And this can connect to ACCG. This can connect to this. So this to this, this to this, and of course the other way around. And basically we just, it's just a graph. And we need to traverse the graph, find the shortest path. Well, I mean the shortest path from the start, which means the shortest number of nodes we need to traverse. Yeah, we'll create a node. So no, just values, right? Just values. Yeah, just values. An adjacency list, right? Adjacency list. So from one, we have adjacency list. We're gonna go to the next one, right? And then from this one, we go to the next one, and we just need to find the first one. We can reach the end and the target. We need to also check the target. Maybe BFS is faster, but it's the same. If there's not, then we just go down and then yeah, let's BFS. Let's BFS. It's just a graph. All right. So what are we doing here? Start, end, and bank, right? Just doesn't matter. So the Q, we need to first create an adjacency list. So adjacency list will equal to, well, it's actually equal to this, right? And no. It's gonna be like this, right? For this in range bank. Range bank, cannot be range bank. In bank, right? So this in bank, we produce this, and then what we're gonna do is for I, G in bank, in enumerate bank, right? We need a target. Oh, we'll get a target anyway. Say if G is equal to end, let's do this. Target equals -1. If G is equal to end, target equals I. Right? Otherwise, not otherwise, and then we need to find for I don't like it. I don't like it. Let's call it N. Land bank. I in range N. If bank I, right? Then for J in range I plus 1 to N. Then we need to see if they are different by 1. How do we go different by 1 like fast? It's a good question. How do we check? I mean, we can use zip. What else? Differ by 1. So we have to check all. So we should say if sum, right, for G1, it's allele 1, allele 2 in zip bank I and bank J, right? And then A1 is not equal to A2, right? So A1 is not equal to A2. That will be false, false, true. So this one, sum this. If this is equal to 1, I mean there's a 1 difference, then we say adjacency list I dot append J, right? And adjacency list J dot append I. They can mutate back and forth. And so this will prepare it, right? I'm going to say if target is smaller than 0, return -1. So we cannot get the target. So target is in it. Now we're going to use, so we're going to go Q. What is the Q? Well, Q is the first step, right? So for G in bank, if this, right? If blah blah blah, and then zip start and G, right? So G in bank, if this, then we put G. Basically, we filter it. So that's the Q, and that's the step. And if not Q, right, return -1. So we cannot even make one mutation, right? So return -1. Otherwise, we say steps equals 1. So we can make one mutation. And then while Q, right, while Q, and then temp equals this. Oh, it's not G. Come on, man. Come on. For IG in enumerate bank, right? And then this is I. I just want index. I just want index. So I'm gonna say for index in Q, right? For index in Q, and don't we need visitors as well? Yeah, it can link back. So visited. So steps is this. Visited equals set Q. All right, for index in Q, for child, right? For child in adjacency list index. If child not in visited, yeah, should be like this. For index, that's the one we check. So it's visited.add index. No. No. What would be the best way to handle this? That's one we visit, right? For index in Q. If index is not in visited, visited.add index, then for this, for child in adjacency list, then we just can do temp.extend, right? Temp.extend. Plus equal to. Adjacency list index, right? Temp plus equal to adjacency this. So we increment, extend temp, or I can just, I think it's fine. Extend its children, and then blah blah blah. Once we're done, Q equals temp, right? And then Q equals temp, steps plus equal 1, right? The second step coming up, and for index in Q, right? If index not in visited, I visit it. I'm gonna do it here. If index is equal to target, return steps. So I increment steps here. Otherwise, return -1. Okay. Let's run this. So start and bank. That answer is 1. That answer is 2. All right, start. All right. Out of 3. So let's start and bank. That will be a minimum mutation. Start and bank. Oh my goodness, that was terrible. Okay, what went wrong? Print Q, everybody. Oh, we didn't hit. Oh, what the? All right, one at a time. Let's check. I in bank, in this, yeah. If bank I equals target, something's very wrong. How about here? Print target. No target? What? Wait, what? I returned. Target is -1. This should be I. Should be 1. Hold on. What the heck? Oh, typo. Typo. People. How could you just not check the typo, man? Alright, try this. Okay. Oh. So build a graph of of all the valid mutations in bank. Then BFS to find the shortest path from start to end, if end is in bank. Should be ON and 40 milliseconds, 20% rank. Alright, what's the overall look like? Best solution, not best solution, 32. Is that DFS? Here's a Q. Suffix. Prefix and suffix. Alright, let's check. Discussion. Same as word ladder. Alright, let's read 2. 2 and BFS. I remember word ladder. That's one of the questions in the Amazon interview. I thought it was difficult, but basically it's just a graph. It's not Amazon? It's Microsoft? I thought it was Amazon. Alright, why do they always have a char set? Maybe that's why I'm slow. Oh, that's true. Bank set. Char set. Level. Visited. Queue. Queue offer. Oh, you don't have to build this. You check every single time? Oh, yeah. I just realized, yeah, you can do this every single time. Current, if it's equal to end, return level, yes. Otherwise, this is to char array. Okay. Current array dot length char old and char set char this equals C. Next equals this. If visited dot contains this and bank set dot contains. Oh, I see what you're doing here. I see. We are literally making change. And that is faster. So instead of building, right, instead of building the graph, which can take a long time because we have to iterate through everything in the bank, what we do is we mutate, we mutate, right? We literally mutate for each letter, right? For each letter, we get the old one and char in char set, we get to the, wait, why do we need the old one? Oh, backtracking here. I see. I see what you're doing. Okay. Yep. I think this is faster. Yeah, I think this is fast because you don't have to go through to create the graph, right? You don't have to create a graph. So I can directly go Q, right? I can directly go Q, steps equals 0. That's actually start. And we can just go, oh, and then bank set, yeah, we're gonna turn that into a set, bank. And then we say for while Q, right? While Q temp equals this for G in Q, blah blah blah. Once we're done, temp equals Q and steps plus equal 1. And then for G in Q, if G is equal to end, return steps. Otherwise, return -1. Okay? So now here, we need visited as well. So visited equals set. So if G is this, return. Right? Otherwise, if G is not in visited, visited.add G. No. Right, now we're gonna go for everything, we just make a change because that's 8. Like only 8. We only have to 8 do 8 times. So when you say for I in range len G, right? And everyone which is mutate. So when you say for mute in TCG, simply just put it in, right? When you say new G, NG equals to G to I plus mute plus G I plus 1 to the end. So we take away the i's, right? We take away the i's and we say if ng is in bank set temp.append ng. Yeah, that's true, right? So temp, I add this, but I don't check for visit because I check visitor here, right? So just blah, 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 push it in, and then once we're done, go up, and popping out. Let's see this one. Ooh, something is wrong. NG's in bank set, I do this, right? Wait, why? For everyone, I mutate, and then it's not, I don't do it. So the next, I mutate, it's non-mutate, so only, so this one mutate, nothing, right? But then I'll go for every single position, and eventually it will push in and go up. How? Where is the stuck? Where do we stuck? ATCG. That's the starting position. Huh? How? Yeah, this is like, and we don't even get into this. So it's like I print this, and then we take this for G. That's weird. The heck? Yes. If G is not in, which is true because initially G is not in, isn't going here. What the heck? G not in as false, but the first one shall be true, right? Yeah, first one is true. Now we add G, right? And then for this, I in range, len G, yeah, so it was 8 for mutation in one of these letters. New G will equal to oh, unbelievable. Typo. Q equals temp. So this is a better way to handle to find links between the genes. Instead of pre-computing all the links, find links on the go by actually making snips. Since the making, right? Since making snips for each gene is 01, right? It's 08. We save on the time that would have been needed to prepare the graph beforehand, especially if bank is huge. Yeah, so this allows us to handle the situation where the bank is small, or where the bank is large. I don't have to worry if the bank is, even if the bank is huge, which will be fine. $28. Yeah, exactly. 83. Okay, so that's the Java solution. No, I don't want Java solution. I want that Python solution because I think the Python solution is very, very short. Okay, we can pop if this returns steps. Bank set are removed. Ah, that, okay. That is pretty smart. That's pretty smart. I can remove it if it's this. So this is not necessary. Right? And then so G, right? Then we just go directly. We don't need this. I range for this ng. If this is in temp this, then bank set dot remove ng. Yeah. We don't need a visited set because we can simply remove remove a gene, right? Remove a gene from the bank to indicate that it has been visited. Otherwise, it's the same, right? But I use the temp. I like this one. I don't want to do like pop. This is a stack. Machine dash mutation in append. Yeah, this is a stack. Has a steps. It's different. It's different. But all right, that'll be it. Pretty good. It's pretty good. Finish it within 1 hour. Oh, a little bit over 1 hour, but that's fine. So tomorrow, I think will be the first day I won't be able to record. Won't be able to live stream because tomorrow I'll be traveling. So I don't even know if I have time to even do the challenge, which I will. I mean, it's fine. I think I'll be able to find time to do the challenge, but not recording. Yeah, recording will be tough. So that'll be it for today. I will not see you guys tomorrow. Adios.